So we are now in chapter 4, and in this chapter we are focusing on classifying chemical reactions. So really our overall goal is to be able to look at our reactants that we're mixing together and to predict the products of the reaction. And what I would do is just pause the video and think about why something like that would be important. I have a few examples here. So just everyday things like bananas oxidizing and them turning brown. Acid-base chemistry we take if we have something like heartburn. So the stomach acid that rises up, the Tums or whatever medicine we take is going to react with it. And we can predict the products of those types of reactions. Another example is when we form hard water. So we have calcium salts that form. So things that we need to know going into this chapter, and one thing I would say is start organizing early because we are going over a lot of different types of reactions and our goal again is to predict the products. So start organizing them early, make flashcards, make a study guide, figure out how best you can organize them for yourself. Things that we need in our toolbox. We want to be able to recognize strong acids. So again, we're assuming that all of these are dissolved in water, but make sure you know these strong acids. And also we need to know these strong bases. Okay, there are other types of strong bases, but for us, we want to know these metal hydroxides. And know that all of them are going to be strong electrolytes. You have one way to remember them here, the letter B for base. Remember that a strong electrolyte means that when I put these into water, they completely split apart into ions. So for example, if I put sodium hydroxide in water, I get sodium with a plus charge and hydroxide with a minus charge. If I put calcium hydroxide into water, I get one calcium ion with a 2 plus charge, and I get 2 hydroxide ions, each with a minus charge. And just a reminder of the pH scale. So acids are going to have a very low pH, and then 7 is neutral, and 14 is going to be basic or alkaline. Something else we need to know is the solubility table, or we don't have to memorize this, we have to know how to use it. I will always give you a solubility table. But it is helping us predict, well, how do we know if something is going to be a strong electrolyte, meaning that when I put it into water, it breaks apart into ions. How do I know that? And you'll always refer to the solubility table. So let's go through how to use it. On the right side, it shows us only the exceptions. So we're assuming that things are soluble in water, or salts are soluble in water, unless we have exceptions on this side. So let's go through it. If we look at the alkali metals, it says that we have no exceptions, meaning that I could pair these cations with any anion. It doesn't matter what it is. I could have lithium hydroxide, I could have lithium chloride, I could have sodium nitrate. It doesn't matter what anion I pair it with, those ionic compounds will be soluble in water. So when something is soluble, we're going to write aqueous next to it. Okay, if something is insoluble, we're going to write S for solid, right? And we have no exceptions. It doesn't matter what I pair it with. If we go down to the next line, ammonium, also a cation. So again, I can pair it with any anion I want and it will be soluble in water. No exceptions. So I could have ammonium nitrate or ammonium chloride or ammonium phosphate. It will be soluble in water. If we go down to the next line, we have nitrates, acetates, and we have perchlorates. All of these are going to be soluble in water. So since they're anions, it's telling me I can pair it with any cation and it will be soluble in water. So I could have silver nitrate. I could have silver acetate. They will be soluble in water. Doesn't matter what cation I pair it with. So we can think of a lot of examples. Now once we go down to the next line, that's when we start to have some exceptions. So for chloride, bromide, and iodide, it says that all of these, when I pair it with some cation, will be soluble in water, except if I pair it with silver, lead, or mercury. We're not going to worry about copper, so we can cross that one out, right? So for this one, I could say something that we expect to be soluble is sodium chloride. right? But something that I expect to be insoluble is silver chloride, because silver is one of our exceptions that makes it insoluble, right? We have fluorides, in general, will be soluble unless I have lead fluoride, okay? And then for sulfate, we have, I could pair it with any cation, so sodium sulfate, potassium sulfate, magnesium sulfate, soluble in water, unless I pair it with calcium, strontium, barium, silver, or lead. Then it will be insoluble in water. We would write solid next to it. Okay, so now if we go down, we have our two switched. All of these will be in general insoluble in water, and here are our only exceptions. So metal hydroxides are in general insoluble in water. Okay, so if I have something like nickel hydroxide or copper hydroxide, it will be insoluble in water. But if I pair that with group 1A, so the alkali metals, if I have something like sodium hydroxide, potassium hydroxide, it will be soluble in water. For carbonates and phosphates, we have the same thing. So in general, they're going to be insoluble in water. Okay, but if I pair it with an alkali metal or with ammonium, it will be soluble in water. So ammonium carbonate or ammonium phosphate will be soluble or aqueous, right? Sulfides in general will be insoluble in water as well, unless I pair it with an alkali metal, alkali earth metal, or ammonia. These ones will be soluble in water. Okay. If we're thinking about things that are dissolved in water, one way that we can express this is using concentration. Okay, so how watered down or how concentrated something is can be expressed as a mass percent. So a mass percent is going to be the grams of solute. Okay, so if I have a solution, I have something that's dissolved in, for us, in most cases it will be water. Okay, the solute is going to be the smaller component, and then the solvent will be the larger component. So if we're talking about a mass percent or any percent, we're thinking of part over the whole. The part will be the smaller component, the solute. For the whole, something to keep in mind is that I have to add up everything because it's the whole. It's the grams of solute plus the grams of solvent. Since it's a percent, it's times 100%. Okay, so something we can use this for is a conversion factor. I would star this one. Okay, when I have a mass percent, I can always assume to use it as a conversion factor that it is grams of solute per 100 grams of solution. And the solution is going to be the whole, solute plus solvent, right? We can also use this with density to convert between mass and volume. Here's an example. And let's set up the have, want, and get there. Now, even if you can solve this problem just by moving the decimal and multiplying it by the number of grams, I still want you to organize the problem, because other problems that we do may have multiple steps. So we are starting with 96.3 grams of solution. And because we're working with different values, so we have solvent, we have solute, we have solution, we want to label everything. Anytime we have a mass percent, it's always going to be used as a conversion factor. So I can rewrite this and put it in my get there and say I have 1.1 grams of sodium chloride. Since it's a mass percent, it's always out of 100 grams of solution. So I have a direct conversion between my solute and my solution, and the question is asking how much or how many grams of sodium chloride. So I already have that direct conversion. I can say I have 96.3 grams of solution, and to make solution cross cancel, it's going to stay on the bottom. I have 100 grams of solution per 1.1 grams of sodium chloride, and then these cross cancel. Now again, you probably just move the decimal to turn it into, or move the decimal point to 0.011 and multiplied it by this, and that would also be correct. But again, once we tackle more challenging problems, it's going to be very helpful to set it up like a conversion factor, always going in your get there. and you should get 1.06 grams. Another way to express concentration is molarity. Okay, so this big M is always going to stand for moles of solute over liters of solution. So it's still part, but now we're expressing it in moles over liters of solution. Okay, and if we look at two examples, usually when we buy something like acid from a chemical supplier, we buy it very, very concentrated. So hydrochloric acid is sold as a 12.1 molar solution, so really, really concentrated. And I would pause the video and think about why we sell them, or why we get them from the chemical supplier so concentrated. Something to think about is just volume, right? If it's more concentrated, I can store a smaller volume, and then I can dilute it or water it down to whatever concentration I want. It makes it a lot easier. So hydrofluoric acid is highly corrosive, right? It's capable of dissolving many oxides, so including glass. So it has to be stored in a plastic container, right? So here's one example. If you are a fan of Breaking Bad, I resisted the urge for a very long time, and then once I started, I binge watched it, okay? Because it's pretty accurate, okay? So Walter White tells Jesse to dispose of this body, right? And he tells him to put the body in a plastic container, and Jesse, being very strong-willed, he just does what he wants, and he decides to put him in the bathtub, and he adds the hydrofluoric acid, and it basically eats through the bathtub, right? So it turns out that the bathtub is made of fiberglass, so the hydrofluoric acid is able to eat through that, whereas the plastic is a polymer, it won't eat through that. Here's an example of another problem. So we have a chemist wants to make a 2.5 liter solution of a 0.100 molar potassium chloride solution. We want to figure out how much potassium chloride the chemist should use. So really what we're asking here is, when you go out into the lab, how much are you initially weighing out on the scale? Let's organize this problem. And something to keep in mind is anytime you have molarity, just like the mass percent, all the units of concentration, you're always going to use it as a conversion factor. So I'm going to automatically put this in my get there. I have 0.1000 molar, and another way, then we can say potassium chloride solution. I always like to rewrite this. So 0.1000 moles of potassium chloride always over 1 liter of solution. Or let's go ahead and write what the solution is. So we have potassium chloride, that is aqueous. Okay, so anytime you see that, it's a conversion factor. Go ahead and rewrite it. And we're starting with 2.5 liters, or we want to make 2.5 liters of a potassium chloride solution. Okay, and the question is asking how much potassium chloride we want to weigh out in grams. So grams of potassium chloride is the question. Let's do a roadmap. For this one, if I start with liters of potassium chloride solution, okay, we can go from liters to moles. So we can go to moles of just the potassium chloride. And just like in the last chapter when we were thinking about what goes into our get there, if I have grams next to something, I still need a molar mass. So let's go ahead and write that out. For every 1 mole of potassium chloride, it is going to weigh 74.55 grams. So something else we can do is now we can go from moles to grams, which is what we want. So we want to go to grams of potassium chloride. Okay, so now that we have that, let's plug in numbers. We start with 2.5 liters of potassium chloride solution. So again, I'm writing aqueous to distinguish between the solution and the solid. We want that on the bottom, liters. So 1 liter of potassium chloride solution and 0.1000 moles of potassium chloride solid. Okay, and then for every 1 mole of potassium chloride, we have 74.55 grams of potassium chloride. And let's make sure our units cross cancel, and we're left with what we want. We have grams here. When we do that, we get 19 grams. So something else we want to look at is how we actually do this in lab. So we would weigh our sample out, our solid, put it into a volumetric flask, and then we have a mark that tells us the total volume we want our solution to be. So we add water up until that mark, and notice that we'd have a little bit of water left over because our solution as a whole will have a certain volume. So something else that's very common to do, again, when we buy different chemicals, especially acids, we buy them really concentrated, so that way we can store less volume, and then we can water it down to whatever concentration we need. And that initial solution that we buy is called a stock solution, and watering it down is called a dilution. So we're taking a 12.1 molar solution, and then we're watering it down to 0.1 molar, which is a lot easier to work with, or a lot safer to work with. Okay, now when we are watering something down, when we are starting with a substance or solution and we're ending with the same type of solution, that is the only time we are using this equation. Okay, so only use when you start and end with the same type of solution. It's such a common mistake. So these are going to be our initial conditions that we're starting with, or our stock solution, our molarity and our volume. Sometimes you'll also see this written as C1V1 equals C2V2. It's exactly the same. And then these are the conditions we want to go to. So what concentration, molarity do we want to make, and what volume of that solution we want to make. So again, stop yourself. Only use this equation if you start and end with the same type of solution. It's so tempting to try to plug this equation in when we're doing a stoichiometry problem. So it's not for a chemical reaction, it's just for watering down. Okay, don't do it. Here's an example. So we have a 122 milliliter sample of sucrose solution. We're given the concentration, and we are diluting it to a final volume of 500.0 milliliters. What is the molarity of the diluted solution? Okay, and we're given the answer there. So let's see how we get to it. Have, want, and get there. So what we want is the molarity of the diluted sample, or the final conditions. So we want M2. Okay, and we've determined that it's a dilution problem because we see the word diluted there. Okay, and we're starting and ending with the same type of solution. Since we know this is what we want, let's go ahead and solve for it. We know M1 V1 equals M2 V2. If we solve for M2, we get M1 V1 over V2. Okay, let's figure out what we already have. We're given the initial volume, so V1 is equal to 122 milliliters, and we're given our initial concentration, which is 1.2 molar, right? Something else we're given is V2. The final volume that we want is 500.0 milliliters. So we're given all the values that we need to plug in. The last thing I would do is just check to make sure your units will cross cancel. So I have volume on top, volume on the bottom. Those units are going to have to cross cancel, which means my units of volume in my have need to be the same. Since they're both milliliters, I don't need to change anything. If they were different units, then I would have to change one of them so they can cross cancel. So now we can solve. We have M2, M1 is 1.2 molar. Make sure you include units when you're plugging this in so you can make them cross cancel. We have 122 milliliters. And on the bottom we have 500.0 milliliters. We get rid of milliliters, we're left with molarity, and we should get 0.29 molar. So here's another problem. Okay, and we should get 319 milliliters in the end. Let's go ahead and organize it. Have, want, get there. Okay, to what final volume should you dilute 50 milliliters of a 5.00 molar potassium iodide solution, so that 25.0 milliliters of the diluted solution contains 3.25 grams of potassium iodide. So what we want is we want B2. Okay. We want B2, and we know this is a dilution problem because, again, we see the word diluted in here. So we can say M1 B1 equals M2 B2, and B2 is M1 B1 over M2. So here are the parts that we do have. We do have B1, which is 50.0 milliliters. We also have M1. We're given the initial concentration is 5.00 molar. And the part that we're missing, so we have M1, we have V1 to just plug in. We're missing M2. So what we need to do is we need to calculate M2 because we're not given that value directly, and then we can plug it into this equation. Let's see the pieces we do have. So we said we're missing M2, but we do know that for the final solution, we are given some information. So we're given that the final solution contains 3.25 grams of potassium iodide per 25.0 milliliters. So now we need to think about this. If I want these two units of molarity to cancel out, I need to get M2 into the correct units. So I need molarity, and remember that molarity is always equal to moles per liter. So I need to make this look like moles per liter. So let's break it into two parts. I need to convert grams to moles, and let's only focus on that right now, which means I need a molar mass. So if I go ahead and calculate the molar mass, I have 166 grams of potassium iodide per 1 mole of potassium iodide. I get rid of the grams, and I'm now in moles of potassium iodide per milliliter. So now I need to take those liters those milliliters and take them to liters. Now I have milliliters on the bottom, so I want milliliters on the top to make them cross cancel. I have 1,000 milliliters in every 1 liter. Okay, and since we're multiplying this whole thing through, even though they're far away, they still cross cancel. So now I have moles on top, I have liters on the bottom, and if I calculate this out, I get 0.783 moles per liter. Okay, or I can say 0.783 molar because these two units are exactly the same. Now I have everything I need to solve for B2 because this is M2, the concentration that was missing. Now to plug in for B2, now I have M1, which is 5.00 molar. I have V1, which is 50.0 milliliters, and now I'm dividing by 0.783 molar. My units of molarity cross cancel, I'm left in milliliters, and when I calculate that out, I get 319 milliliters. So that brings us to our first type of chemical reaction. So this is called a precipitation reaction, also known as double displacement. Some books also say replacement, okay? But it's a type of reaction where I'm forming a solid. So the formation of calcium salts that form things like hard water or kidney stones are different types of calcium salts, usually calcium oxalate. But we can predict, based on what we're mixing, if we're forming a solid or not by looking at the solubility table. Right? And then we can also figure out the degree of water hardness in another set of concentration units, so parts per million. But for a precipitation reaction, again, it's a double displacement reaction. Another word for it is metathesis. And what we're looking for to know that it is a precipitation reaction is I'm looking for two ionic compounds. Okay, two ionic compounds are two aqueous solutions of those ionic compounds, and then I know I'm doing a double displacement or precipitation reaction. We are going to switch partners. So the anion of one is going to pair up with the anion of the other, and same, the cation of the other is going to pair up with the anion of the first. Okay, something we want to keep in mind, and that's a very common mistake, is the subscripts that we have for the ionic compounds on the reactant side do not carry over to the product side. We have to figure out charge balance. So that's something I would star or underline in your notes. We have to refer to the solubility table. So we're switching partners, we're forming two new ionic compounds, and then we go to the solubility table to figure out if they dissolve in water, aqueous, or we're forming a solid. Okay? We have to form a solid for a reaction to have take place. Something else we want to keep in mind is we're going to write different types of reactions. So a whole molecular reaction that shows everything, a complete ionic equation that shows everything that breaks apart into ions, and something we want to keep in mind is that only aqueous substances split apart into ions. So again, aqueous means that I have a strong electrolyte. When I put it into water, it splits into ions. We want to leave solids, liquids, and gases exactly the way they are. You don't split any of those apart. And then a net ionic equation is where I've crossed out all spectator ions, or ions that are on the reactant side and the product side, meaning they're not doing anything or changing. Here is one example of solubility and what allows something like table salt to be soluble. Okay, so thinking back to the solubility table, and what happens is you have a very strong solute-solvent interaction where the chloride ion interacts with the partially positive hydrogens on the water, and the sodium interacts with the partially negative oxygens on water. And that solute-solvent interaction is much stronger than just the plus and minus of the sodium and the chloride coming together. Now, something that's insoluble in water has strong what we call solute-solute interactions, or we can say that ionic bonding is very strong. Okay, so what I want you to do is pause the video, look at your solubility table from the slides, and figure out if these are expected to be soluble in water, aqueous, or insoluble, solid. And there you go. Okay, also get some practice with writing formulas. So let's go through the types of equations. Let's put these words into an equation. Solutions of sodium iodide. So I know that sodium has a plus charge, iodide has a minus charge. So I have sodium iodide, and solution of implies that it's aqueous. And we're going to mix that with lead 2 nitrate. So I have lead, and I need 2 of the nitrates with a minus charge to balance it out, and it's also a solution. Okay, so now I want the sodium to pair up with nitrate ions, and I want the lead to pair up with iodide ions, keeping in mind that these subscripts don't transfer over. I need to say that sodium has a plus charge, nitrate has a minus charge, so when I bring those ions together, what I get is NO3. And then lead has a plus 2 charge. I'm pairing that up with iodide, so that is going to be 2 iodides. All right. The next thing we want to do is go to our solubility table to figure out if these are soluble in water or not. So sodium nitrate is soluble, so I write aqueous next to it, and then lead iodide is insoluble, we write solid next to it. Okay, the next thing we do is we need to balance our equation. So I have 1 sodium here, I have 1 sodium there. I always start with my metals. I have 1 lead here. I have 1 iodide here, but 2 here, so I need a 2 on this side. And that also changes the number of sodium. So I have 2 here, which also means I have 2 nitrates. Remember to balance the polyatomics as a unit, and I have 2 nitrates here, so I am balanced. The next thing is we want to write our total or complete ionic equation, and we're only going to split the substances that have aqueous next to it. And we want to keep in mind the number of those ions we have. So this 2 means I have 2 sodium ions. I have 2 iodide ions. So let's go ahead and write that out. I have 2 sodium plus, since they're ions, we have to write the charge, and you have to write that it's still dissolved in water. The 2 distributes to the iodine as well. So I also have 2 iodide ions, right? This is also aqueous, so we're splitting it. We have 1 lead ion with a 2+ charge dissolved in water. And then this 2 tells me I have 2 nitrate ions. So that 2 will now go out front here, NO3- aqueous. And then I'm going to draw my arrow here since we're running out of room. The sodium nitrate we will split apart as well, so I have 2 Na+ aqueous, and the 2 distributes to the nitrate as well, so I have 2 NO3- aqueous, and the lead iodide stays exactly how it is because it's a solid, so I don't split it apart, I don't do anything to it. And the next step is, for the net ionic equation, I want to go back and I want to cross out any ions that are the same on the reactant and the product side. And it's because if it's the same, it's not actually doing anything in the reaction. So sodium is exactly the same. Nitrate is exactly the same. It means they're not actually doing anything, right? Everything else you did not cross out, you bring down. So 2 iodide ions react with 1 lead 2, and we produce lead iodide as a solid. So a chemical reaction occurred. So here is a problem that I want you to organize, and we'll talk about more in class. So let's just talk through it. What volume of potassium phosphate solution is necessary to completely react with 134 milliliters, and we're given the concentration of a nickel chloride solution? Very first thing I would do is, we know we're doing a chemical reaction. It's not a dilution, so write out the equation, right? We're given the concentration of one, we're given the volume and the concentration of another. Both of these concentrations, remember, we can write those out as conversion factors. So I would start there, and then we'll talk about it in lecture. And you should get 4.45 milliliters. Here's another example. So again, we have another chemical reaction happening. We're saying mercury nitrate is reacting with sodium sulfide solution. And how many grams of mercury 2 sulfide form? So in this question we're being asked for grams, so we know we're going to need a molar mass somewhere. Again, you're going to start with your balanced equation. You're going to figure out what you have. For both of these concentrations, those are automatically going to go in your get there. We're using them as conversion factors. And since we want grams of mercury sulfide, we need to have a molar mass of that. And we should get this. Right? One more way to organize this problem is also doing the reaction or ICE table, where we're putting everything in moles. We're figuring out what is limiting, so we're using up all of the mercury nitrate, and we're using up only part of the sodium sulfide, so we can see how much we have left. And then we can also, initially we have no product, we can see how much product we're forming, and how much we have at the end. We can always convert it to grams. So just another way of setting up the same problem.